Let me guess, your acid and base test for AP Chemistry is tomorrow, and you need to cram. Well, you've come to the right place, because today we are going to learn everything you need to know about acids and bases. Let's start off with the basics. What are acid and base solutions? Well, an acidic solution has a high concentration of hydrogen ions, and a basic solution has a low concentration of hydrogen ions. Acidic solutions tend to be your everyday orange juice and gastric acid, while basic solutions tend to be your cleaning products like bleach and soapy water. The Bronsted-Lowry definition of acid is that an acid is a proton donor. This means it donates a hydrogen ion to a base to create the conjugate base. Acids also have a tendency to turn litmus indicators red and react with metals to create hydrogen gas. An easy way to identify an acid is through its relatively low pH. Acids also react with carbonates to produce salt, water, and carbon dioxide. There are two types of acids: strong and weak acids. Strong acids dissociate completely and have a lower pKa than weak acids. It can be handy to memorize a list of strong acids in the list here for your AP Chem test. The second type of acid is weak acids. Weak acids are acids that do not dissociate completely and are all acids that are not identified as strong. Bases are defined as Bronsted-Lowry proton acceptors. This means that bases accept protons from acids to become the conjugate acid. Some properties for bases are its tendency to turn red litmus paper blue, have high pHs, taste bitter, and are slippery. Bases also have neutralized acids producing salt and water. Just as the acids, there are strong and weak bases. The difference between the two are that strong bases are irreversible because they dissociate completely, while weak acids are reversible because they do not dissociate completely. Neutralization is an important concept in chemistry that states that acids and bases react to form water and salt. This can be viewed in the reaction between HCl and NaOH. When the spectator ions are cancelled out, you are left with H2O. It is important to note the results of combining different variations of strong and weak acids and bases, as seen on the curves on the right. When combining two strong or weak acids and bases, the pH is neutral. If a strong acid is added to a weak base, the pH is less than 7. When a weak acid is added to a strong base, the pH is more than 7. The last concept that you need to know for acid and bases is titration. Titration is the use of a flask and burette to combine an acid and base through intermittent drops of solution. The flask must contain an indicator when titrating to record sudden changes in pH. In order to review titration curves, let's go through a titration problem. Suppose 13 milliliters of a weak acid with a molarity of 0.1 molar is titrated with a 0.1 molar NaOH solution. How will we draw this titration curve? The Ka and Kb is provided to you. To start this problem off, you must first create an ice table. Because x molar is removed from the initial concentration of 0.1 molar HX, you must add x molar to the other side of the reaction. Next, you must find the initial pH. Using the ice table, you can determine the Ka is x squared molar over 0.1 minus x molar. This is equal to the given Ka of 7 times 10 to the negative 3. If you solve for x, you can get 0.23 molar. Next, you must input this concentration into the pH equation to get the initial pH of 1.64. Next, you need to find the pH of the neutralization halfway. In order to find the pH of neutralization halfway, you must divide the volume by 2. By dividing 13 milliliters by 2, you get 6.5 milliliters. Using this number, you can solve for the moles of hydroxide. 6.5 milliliters times 0.1 molar equals 0.65 millimoles of hydroxide. Using the amount of the moles of hydroxide, you can solve for the moles of acid. 10 milliliters times 0.1 molar equals 1 millimole of HX. Now that you have the millimoles of base and acid, you can input the numbers into the Henderson-Hasselbalch formula. By solving the formula, you find that pH equals pKa. This means that the weak acid is 50% neutralized when pH equals pKa. The fourth step to this problem is to find the equivalence point. To do this, you must first divide 0.01 molar by 2, which equals 0.05 molar of HX, which will be your initial value in a new ice chart. By inputting the value into the ice chart, you will realize that you have to subtract X molar from the reactants and add X molar to the product side. After filling up the rest of the ice chart, you can input the numbers into the Kb equation, which is products over reactants. This will result in X squared molar over 0.05 minus X molar. Next, you must solve the POH equation, which is log 10 2.67 times 10 to the negative 7, which equals 6.57. After getting 6.57, you can subtract that from 14 to get the pH value. The final step to this problem is to find the pH after more NaOH is added past the equivalence point. To do this, you must first solve for moles of hydroxide. Since the half equivalence point had a volume of 13, you must input a volume that is greater than 13. In my example, I inputted 14 milliliters. You must multiply 14 milliliters by 0.1 molar to get 1.4 millimoles of hydroxide. Then solve for the moles of acid. 10 milliliters times 0.1 molar equals 1 millimole of HX. Next, you must input the values you have obtained into the ice chart. By subtracting negative 1 millimoles from the reactant side, you must add 1 millimole to the product side. Finally, you must divide 0.4 millimoles by 10 milliliters, then add 14 milliliters, which equals 0.17 molar, which would result in the hydroxide concentration. To find the POH, you must input this number into the POH equation, which would result in 1.8. To find the pH from this value, you must subtract 14 by 1.8 to get 12.2. Having obtained all necessary points, you may graph the titration curve and label the equivalence point, finishing up the problem.